All right. Otherwise, we'll go ahead and get kicked off with our first speaker, which is Jonathan Flinn from DNVGL. And he's going to be giving a talk on modern distribution planning. Jonathan Flynn's been with DNVGL for 14 years and came over from our energy advisory practice and has been working with our consulting group for a couple years. I'll go ahead and read his bio so I don't sell him short here. His primary fields and related to renewable energy. The last 7 years, most of his work has been involved in studying the impact of distributed renewable energy generation on transmission and distribution systems and support for interconnection applications with several U.S. utilities. This work has involved in creating and modifying system models in both a static and dynamic software, creating high penetration PV studies for analysis, analyzing the system to identify technical limits on further PV integration, identifying potential mitigation options for utilities, and running cost-benefit analysis for new DER technologies. So very topical for this group. So with that, I'm going to turn it over to Jonathan Flinn.
Just go up here. Yeah, that's fine. All right. Okay, thanks, Kyle. Morning, everyone. So yeah, I'm going to talk this morning about, oh, here we go, about modern distribution planning. So this is based on some, I work in DNVGL's consulting team with Synergi Electric. So this is based on some work that we've done with clients over the last few years. And there are some trends involved. So basically, what is driving a lot of the modern distribution planning process is really two things, or at least the things I'm going to talk about today. So one is to move to automation and big data processes. A lot of that is driven by what Julio Romero was talking about yesterday, because we start to have a lot of distributed generation on the distribution system. So we need to have new tools, new processes to address that, and everything becomes a little more complex than it was. So there's a few topics I'm going to talk through in modern distribution planning today. One is the time series analysis. We have something on load profile development, DER modeling processes, analysis processes, and then mitigation, non-wires alternatives. A lot of utilities now have to deal with non-wires alternatives and non-wires solutions. And then a last part on hosting capacity analysis. So I'll get straight into the time series part. So there are a bunch of different drivers for utilities to move to time series analysis with the distribution system these days. The primary one, I think, is the interactions of load and generation, which makes things a lot more complicated than it used to be when you could just look at peak load. We also have some issues around load analysis, load management, some new opportunities there. And then similar with generation analysis and new things that we can do with control and management of generation. And then the last part is something that we've been looking into more recently is how the variable generation can impact the LTCs and the lifetime. So starting on interactions of load and generation. So this is a net load profile measured at a SCADA meter at a substation. So anyone that's worked with DER recognizes this curve. It's basically a duck curve. So you can see there's some generation involved in here with the dip during the day and then the peak in the evening. But back in the day, we would just be able to look at this and say that's our peak load, 20 megawatts happens at, I don't care what time it happened at, I'm just going to analyze that peak load and make sure our system can deal with it. And that was fine as long as there was no generation on the distribution system. We could trust that this is the load that was actually being used out there. There was nothing else really involved. Maybe there's some capacitor banks that deal with, have some local voltage issues. But otherwise, we could just trust that that is the load that's actually used on the system. Then when people start to have some generation on there, we might be interested in what the minimum daytime load was, and still we might just analyze those two locations, but it's still a fairly simple analysis. But now we have so many different kinds of generation on the system, we need to know really what the generation was doing when we measured that load or make assumptions about it. And we need to know what the actual customer load was. So what's happened here is we've gone from the net load profile, which is the green curve there, which includes the effects of both load and generation. We've made an estimate of what the generation was, which is the light blue here. So that's a PV generation profile. And then we have to add that back into the net load to find out what the actual load the customer was using was. And that gets us this dark blue curve. So when you look at the dark blue curve, which is the actual load the customer was using, we can see in this case the actual peak load was 22 megawatts instead of 20 megawatts. So it's 10% higher. And if the customer used the same load on a different day when there was less solar generation, we would have to deal with that 22 megawatt load instead of a 20 megawatt load. Also, we can see that the minimum load is actually a little higher than we saw from the net load profile. And that's also worth knowing as well. So these more complex interactions of load and generation make it more difficult to just say, these are my critical times, this is a peak load, this is a minimum load. We can't really do that anymore. We need to look at the whole day profile. And there may be other generation. In this case, we're only looking at a solar generator. We could have battery storage on there. We could have other forms of generation. So it means that we have to analyze more orders of magnitude of different time steps. And that's why Larry has created all these 8760s and 576 analysis processes in Synergi. But it causes us to have a lot more data points to look at. So next is on the load analysis and management. So this is taken from the same set of data. So we can see the peak loads from looking at the net load profile was about 20 megawatts. And when we looked at the actual load the customer was using, the peak load was 22 megawatts. So when utilities start to look at multi-year analysis, then we start to look at load growth. And then it's important to know what load we're applying the load growth number to. So if we apply a load growth of 5% on this feeder, if we added it to the net load profile, we'd be adding 1 megawatt, but really we should be adding it to the actual load profile, which is what the customer is using. Then we have 1.1 megawatt. An extra 0.1 megawatt on a 20 megawatt system is not a huge deal, but if you compound it over 5 years, 10 years, then it starts to become important. So it's important that we know what the actual load the customer was using was for that reason. Another reason is because we have all these new opportunities with demand side management, demand response programs, using energy storage to manage the distribution system. And for those, we need to know what was happening through the whole day, because we need to know the charge and discharge cycles of energy storage systems. We need to know the times of day when we can start to use demand response programs. They may be based on industrial equipment, they could be based on thermostat settings. So we need to know how those are going to impact the load throughout the day. And then again, it's important to know the time-based value of the load as well as the actual value. Okay, and then similarly on generation, there are new opportunities if we start to look at load profiles. So this is a hosting capacity analysis throughout a day on one section of a feeder. So this tells us how much generation we can install on that feeder each hour of the day, or how much generation we can have output on that feeder at each hour of the day without having any upgrades. So normal process for most utilities still is just to take the minimum value and say that's your hosting capacity for this section. You can't install any more than that. And that gives the utility some confidence because they know that there are going to be no upgrades involved. But we are missing out on all of this generation that we could have in the evening, still without any upgrades. So if we can do something more sophisticated with the generation, we may be able to allow the generators to install more capacity of generation as long as they comply with this time-based profile. So here's an example where we took the same curve and we used the hosting capacity using the minimum hosting capacity value of 3 megawatts. And the generator could produce this kind of output profile in the dark blue curve there. But if we allowed them to install 6 megawatts, they may have to curtail for a little part of the day to comply with that hosting capacity curve. So those blue bars that are sticking up there are how much energy they're losing through curtailment. But they would be able to produce all this extra energy at different hours of the day. And the cost-benefit calculation may work out for them. So it gives our customers some more options, possibly, if they can work through a time of day profile or use different signals to control their generator. Okay, so the last part of the drivers for the time series analysis is on LTCs. So we've been working on some new processes and new methods recently to try and calculate the impact of variable generation on load tap changers. So the issue is that when we have variable generation on the system, the amount that it changes the load flow through the LTC can cause the LTC to change positions. And if we have a particularly cloudy day when there's clouds coming and going, and there's a lot of generation on the feeder, we can have a few different changes in the tap changer. So this is what this chart is showing here is we did 2 analyses for a full day of operation. One was with the PV at 100% throughout the whole day, and that's the green line here. And the other one was the PV off, and that's the dark blue line on the top. And we did that to see how far the PV could move the LTC between being off and being on 100%. And then we combined that with some irradiance data to figure out roughly how many extra tap changes we could see throughout a year on this LTC. So that's it's a little difficult to work through this process. It's something that we're still working on developing. The other aspect to this is that the other thing that affects LTC lifetime is the current through the LTC when you change the contacts. And we need to include that into this analysis as well. At the moment, it's just the number of extra LTC operations that you might see, and you can compare that to what you would have without generation. But we want to avoid getting to a place where we have to analyze every 30 seconds of load on the system, because that's a huge amount of extra information, and it'll slow down the analysis a lot. So this works with just the 576 or 8760 analysis. Okay, so next is on load profile development. So we've been working with a few different utilities on helping them to develop load profiles in Synergi based on either SCADA data or AMI data, or a combination of the two. So our objective is to develop the representative load profiles that we have in Synergi based on whatever data we have from the utilities. The data that we get to use to develop load profiles varies between utilities, and even within utilities, different feeders can have different kinds of data. So we need to develop processes for all of them. But this is what we're trying to get to, is the actual customer load profile, rather than just using net load SCADA data or even just AMI data. So there are a few different profiles that we want to develop in Synergi. Sometimes we need just a pair of these, and sometimes we might want all 4. But normally the critical ones are the peak load profiles. So we have a peak load profile for each month of the year, which is the maximum customer load at each hour of the day in that month. We have the minimum load profile, which is the minimum load for each hour of the month. And then weekday and weekend profiles, those say the same thing. Those should be different at the end. Weekday and weekend profiles are just the average load profiles for each hour of each month. So those are the 4 that we're trying to get to. And like I said, we work with different data from different utilities and within utilities. So there are a few different data points that we might have. One is the SCADA data that comes from the substation. And that is really just the net load that we have from the whole feeder. So we have to make some assumptions about how that load is distributed on the feeder, how it's allocated. And we probably have to make some assumptions or some calculations about what generation was doing at the same time. Next, we might have some AMI data. So that provides us a lot more definition, resolution than SCADA data, because we know what the distribution of the load was, what the load allocation was at any time. And we can proportion the load to the customers more accurately based on actual load from the customers. Then on the generation side, when we're trying to figure out what the generation was doing, or make assumptions about what it's going to do in future, we can take irradiance data. So it provides us just the solar output. And we just have to assume things about the tilt and the shading of the generators. Normally, we assume it's just a direct correspondence between the irradiance and the generation output. But there are some assumptions involved there. What is better is if we have actual PV output data from the generators. So then we don't have to make any of these assumptions about tilts or efficiencies of the generators. There's also the problem of if we have oversized DCs or oversized inverters. If we're just using the irradiance, then we might not have that information. But if we have the actual PV output data from the plants, then we can see if they're clipping throughout the day or if there's any other issues. And that's useful when we're looking at historical data. So this is just some text, which is basically what I just talked about, but I'll go through some of it. So with the AMI data, again, we get more granularity. It provides a lot of detail for utility load research teams, so it's useful for them. The other thing we'll talk about in a second is switching. With AMI data, we don't have to be so concerned about that because the customer is using whatever load they're using, regardless of which feeder they're switched onto usually. Whereas with SCADA data, we do have to take care of this switching problem. On the disadvantages with AMI data, there's just a huge amount of data that we have to get through. So trying to use all of it is not always easy to do. Whereas with SCADA data, there's much less data, but again, we have to make these assumptions about allocations and distributions. And then on the generator side, we have, again, the generator meter data is ideal if we can get it. Problem is that if you have every single PV generator meter, then it's expensive for the utility. Irradiance data is easy to get, or easier to get. Usually we can have a single data source for a substation or a feeder, or even a whole utility sometimes. And again, we just have to make these assumptions about the efficiency of the generator. And then the last set of data that is probably the most commonly used that I've seen is just using irradiance data based on your latitude and longitude, which is data we can get from Synergi. It's free, it's easy to get, but there are some fairly coarse assumptions involved in that because we usually have to assume either it's a clear sky day or there's no PV at all. So it ends up with some fairly conservative assumptions if we use that data, but at least it's easy to get. So in an ideal scenario, I think we would be using AMI data from the customer and actual PV output data to figure out our load profiles, because then we know exactly what was going on the feeder. We don't have to make any assumptions really. And we can figure out exactly what the actual customer load was, what the generation was, what the net load was. We know everything we need to know. But that is the most expensive approach because we have meters at every customer, we have meters at every generator. So it doesn't happen very often. This is the more common scenario where we have just SCADA data at the substation, and then we have to make huge assumptions about what the PV was doing based on just some irradiance curves, probably from Synergi, maybe from elsewhere if we're lucky. So that represents some challenges and some discussions about assumptions when we're making the profiles. So the assumptions that we have to make when we're dealing with generation is we have this net load curve, probably from the SCADA, which would be the light blue area here. And then we have to figure out how much generation we're going to add back into that to get to the actual customer load curve. And we can, if we're dealing with just this kind of irradiance curve from Synergi, which has no link to what historically happened, then we're just going to assume the worst case to make it conservative. So when we're looking at the peak load curve, we might assume there's a clear sky profile, the maximum radiance that we could have for that month of the year, add that back into the load, and we get this dark blue curve on the top. When we're looking at the weekday and weekend profiles, we might take the average irradiance for the month. And then we are adding a little less generation in to the load profile. And then for the minimum load, we might assume there was no generation on that day. So we don't add anything back into the load and we end up with the lowest possible load profile. So those are conservative assumptions based on not knowing anything really about the irradiance when the measurements were taken. So next is on the data screening. So I mentioned a little bit earlier this problem that we have with using SCADA data, that we don't always know the switching status of the circuit at the time the data was measured. So here we have an example with two circuits, orange circuit, which is we'll call M1, I think, M1, and the blue circuit M2. So in this case, they're both operating, they're isolated, and there is an open tie switch between them. And we know that the data we're measuring at the 2 meters is just the data for those feeders in normal operation. But when we have M1 switched out for maintenance or something, we open this switch at the top, we close the tie switch. Now all of feeder 1's load is going through the meter for feeder 2. So we end up with, if we just looked at the SCADA data, we would see a high load on meter 2 there. but it's not really representative because it's not just feeder 2's load now, it's feeder 1 and feeder 2. So we need some kind of screening method to figure out when that happens. And we don't always know what the switching status was on all the circuits when we're just looking at load data. So we've tried to come up with some approaches to deal with this. So the best option is if we know exactly what the switch status was for each feeder and we had some kind of marker that would say this is normal operation, this is abnormal operation, then that would allow us to screen the data. But that doesn't happen very often, or at least the data is not kept together. Another option is to use some fairly rigorous statistical approaches to identify outliers in load data. There are complications with that because peak loads are already outliers, so you might end up just screening out all of your real peak loads. And then alternative 3 is to use some other data source as an indicator for when we would expect to see high-end loads on the system. And this is the one that we've been working with recently, is using some other data. So so what we came up with for this project was to assume that peak loads are caused by people using heating and cooling equipment. And those may not be the biggest contributor to the load, but they're the part that causes it to be very high or very low. And that's our assumption in this case. So we need some way to figure out which temperature we might expect to see a lot of heating or cooling equipment used at. So we started looking into thermostat settings in different utilities. So we developed some profiles of what settings people put their thermostats at, where they have it cooling, where they have it start to heat. And then we cross-referenced that with some historical temperature measurements that we get from weather websites. And we use that to figure out when we would expect to see peak loads. So then we can look through the load data. And if we see a peak load, we can check that it coincides with one of these very high temperature times or very low temperature times. And if it doesn't, if we had a temperature that was a very mild temperature on that day, and we had a peak load, we could say maybe that peak load is not valid. And this is making some assumptions still, but I think it's a logical approach, and it should make some improvements in the data that we're using. So that's what we're using to screen the data and trying to figure out trying to screen out these cases where we have switching on the feeders. And this is all, the intention of this is to make it all automated so that we can just take a dump of SCADA data from a client. We put in our thermostat settings, we take a temperature profile from some publicly available data or some local data, and then we can just produce the load profiles that are prepared already for import to Synergi. And it should be all very quick and very straightforward for the utility. Okay, so next is onto the DER modeling and DER analysis that we deal with utilities these days. So like I said at the start, when I started working 7 years ago, we were just starting to get into looking at generation on the distribution system. So before that, we would just look at generation as negative load because it wasn't making a huge impact on the system. We could just see what the net load was and we'll deal with that profile rather than actually looking into what the generation was doing. So there was still not really any advanced analysis involved in it. But then between 3 and 7 years ago, we would start looking at modeling generators individually, so we could start making assumptions about what they might be doing. And then processes for hosting capacity became more sophisticated, and we have more involved impact studies as well, because we can start to look at using the generators to provide mitigation. And now we start to look at generators with advanced control functions. We look at volt-var curves, volt-watt curves, different power factor settings. We can look at coordination between different generators on a feeder, and we can start to use them for non-wires alternatives, so as mitigation as well as causing impacts on the system. So that's how things have progressed up to now. So there are some different controls that we look at. The good thing about the advanced control functions is a lot of the time it allows the generator to solve the problems that they cause. And that's ideal for the utility, it's ideal for the generator, and it's usually the least cost approach. So when we look at passive controls, we can have time of day settings. So the good thing about time of day settings is usually the customer knows what their losses are going to be when they're curtailed, when they're not. But we may, as the utility, if we're going to rely on the customer to impose these settings, we may want some kind of verification that it's happening. So the utility may need to start investing in ADMS for a lot of these technologies. But it does provide the benefits of increased hosting capacity for the utility, and it allows the customer to avoid upgrade costs if they can comply with those time of day settings. And we can also use non-export limits. So again, there'll be some losses to the customer, possibly because they can't just have their generator running as it would. And there may be some additional equipment involved for the utility to have some assurance that it's not going to export. There may be some additional relays. But again, it provides some benefits for the utility in terms of mitigation of the DER impacts and the low upgrade costs. So we can look at those both in Synergi already. We can apply time of day settings through DER profiles or irradiance profiles for a generator. And we have now the non-export option in Synergi. So the load at a customer and the generation will be tied, and the generation will not exceed the local load. Next is on the active controls. So we have volt-var controls that we can apply advanced inverters. The good thing about that is that there are negligible losses for the customer, usually as long as they have enough inverter capacity to comply with the volt-var curve. But again, the utility may need to invest in some ADMS systems. And as before, it allows the utility to increase the hosting capacity for generation on the system. And also potentially, if there's a lot of generation out there, it can improve the voltage profile on the feeder. Volt-watt control is fairly similar, except it's usually more applicable to energy storage than PV. You could use volt-watt and PV in the downward direction, probably less so in the upward direction. But again, it provides some increased hosting capacity for the utility. So again, those are things we can already apply in Synergi. We have the volt-var curves and volt-watt curves that we can put on advanced inverters and just let Synergi run with those. And then last is probably even more advanced than those is the coordinated controls. So we have a bunch of different generators on the system working together or working in a coordinated manner to address a problem. So it means we can mitigate, we may be able to mitigate overloads, we may be able to mitigate reverse power flow problems by having some way of controlling all of the generation together. So it depends how this is managed. It could be managed by the utility, it could be managed by a third party that is contracted with all of these generators. So the costs are dependent on how it's managed. There may be a ADMS or DERMS system for the utility, or they may just have to pay a coordinator to deal with it. Cost for the customer is possibly curtailment or reduced output at certain times. But again, it allows for increased hosting capacity if we can mitigate these overloads or reverse power flow problems. Then we have smart EV charging. So in this case, we'd be looking at trying to coordinate it so the EVs are being charged at the same time as we have excess generation from PV. That's the reason that doesn't often happen naturally is because people want to come home and charge their cars at night when we don't have any PV output. So it may involve some increased charging costs for the customer if they want to charge in the evening. But we could use different levers to try and encourage them to charge during the daytime. And again, there would be some management costs for the utility, but it could reduce upgrade costs for EV charging if we can kind of kill two birds with one stone by having the EV and the PV time to coincide. And then these last two are kind of combined. So here we're looking at a bunch of different generators or energy storage systems on the distribution system bidding into the wholesale markets. So they may be working in the frequency regulation markets. They may be providing some other ancillary services to the utility and getting payments for that. But the problem with that is that the requirements for bidding into those markets and what we want them to do for the distribution system may be in conflict. So being able to figure out what cases to analyze there, what limits there might be on there is not easy to do. because if we limit what the customer can do to bid into these frequency regulation markets, they're probably not going to be happy with that. But we need to manage the cost on the distribution system as well, and make sure that we don't just have all of our generation outputting at the same time and causing more problems than it solves. So those last two are kind of newer problems. In some cases, there aren't problems because a lot of places don't have frequency regulation markets for storage yet. But it's starting to happen in California at least. Okay, so next is on some modern DER impact study processes. So a lot of you already deal with DER impact studies. It's probably one of the older studies that we do with DER. So here we'd be just looking at the impact of single DER facilities on the distribution system, trying to figure out if they cause any technical violations and any associated upgrades that might need to be produced. So the impact study itself, we might just assume that the output from the plant is maximum, so we have the maximum impact. We can do the time-based profiles and do 576 or 8760 analysis in Synergi, and then we just identify any violations caused, and that all comes out of Synergi, and it's a very simple process. The data is already there. The next part is starting to use the DER as mitigation, either for the impacts that they've caused or for some other violations that we've seen from our planning studies. So this is what some utilities are trying to do now, is to take as much advantage as they can of the DER in the system. But we need to make some assumptions, and we still need to be conservative about what the DER can do. So if we were planning to use PV as mitigation for a thermal overload, for example, we can't assume that it's going to be a clear sky day every day, because it's not going to happen. There are going to be days when there's very low irradiance. So one assumption we might make is to assume a minimum irradiance profile rather than a maximum irradiance profile. We may make assumptions as well about the availability of the generators. So if we make those conservative assumptions, a lot of the time it's hard to get a lot of value out of the DER for mitigating these problems. But it's a process that some utilities are looking at and starting to use. And if there are ways to increase the output, or if we had storage on the system, then we could include that as well. And then the last part that, again, we might look at an impact analysis that hasn't been looked at, I think, so much, is, again, this impact on the LTCs. So I think I discussed most of this earlier. I'm not going to spend a lot of time on it here. But again, the problem is that if we have a large amount of variable generation on the system, we can cause more wear on the LTC just due to extra operations. So we have developed an automated process to do this, to figure out roughly how many extra operations we might see on an LTC over the year. And it's a combination of the output of the 576 or 8760 analysis with some kind of high resolution irradiance data that we have to figure out the ramps up and down over 30-second intervals. So we can use that to figure out the extra number of operations. Okay, so on the impact study process, this is fairly straightforward. I think most utilities follow the same process now. So we start off with just a baseline analysis, a pre-project study, figure out if there are any violations that have to be caused without the PV first. Then we add in the PV and see if there are any new violations, or the DER, and figure if there are any new violations on the system. Then we can attribute those to the DER project. If there are no new violations, then everything's good. We can report to the customer that they can install their generation. But if there are violations, then the first step is to see if we can fix the violations just by control of the project. So then we can start to look at different power factors, volt-var regulations, and curtailment if none of those work. And if those fix the problems, then again, we're all good. There are no upgrades required. But again, if there are still problems that we can't solve by just the generator itself, then we have to look at upgrades. So what we can do now is automate a lot of this process. So the impact study processes are standardized, they're fast, they're efficient. The customer is happy because everything comes back to them quickly. Utility is happy because everything is done in a standardized manner, and we can reduce the amount of resources we use. We can use these new advanced control functions to provide cost-effective mitigation on the system. So those are the changes that are coming with impact study processes, is as much automation as possible, and using the new technologies and new analysis processes on the system. So on to mitigation and non-wires alternatives. So I think a lot of utilities nowadays, when they're doing their planning processes, if an upgrade is required, then in some cases you may be required to look at like a non-wires alternative solution. No matter if you know that it's not going to be cost effective or not, we still have to address them. And the costs are coming down, so at some point I think they may become even more cost effective than they are at the moment. So this is a simple mitigation process that we might see if we're looking at a planning study. So typical planning study will involve planning for load first, load growth violations. Then we may have some thermal overloads, we may have some voltage violations. Normally it makes sense to address the thermal overloads first, and then the voltage violations, because a lot of the time the mitigation that we apply for a thermal overload, like reconductoring, can improve the voltage and we don't have to do anything else. So that makes sense to address those that way. And then once we've addressed the load growth violations, then we can start to look at the DER impact violations and see if there are any upgrades required there. So there are a bunch of different options that we have for voltage violations or voltage mitigation, thermal overload mitigation. And we can select which ones make the most sense or which ones are likely to be cost effective. So what we need to do is prioritize which mitigations, which order we look at things in. So our objective is to mitigate all of the violations that we see in our planning studies at the lowest total cost to the utility. And what total net cost means is a combination of all the costs and all the benefits. And there may be some iteration involved because we need to know which order we can do things in, and sometimes produce a roadmap. So this is what I mean by the prioritization. So this is an example from a planning study where we had 2 violations. This is a multi-year study, so each of these is a different year in the study process. In this case, we had 2 violations. We had a voltage violation that occurred in year 3. And if we were just looking at that voltage violation on its own, we came up with a new voltage regulator, $110,000. Then in year 5, we saw a thermal overload that we had to mitigate. That's $500,000 of reconductoring. So if we just looked at these 2 in isolation and mitigated them this way, the total cost was $610,000. But if we go back to that voltage violation and we look at using the reconductoring that we would have done anyway in year 5, see if that can mitigate the voltage problem, and it did, then we can do that reconductoring earlier, mitigate both problems, and we only have to spend $500,000. We have to spend it 2 years earlier, but it saves us over $100,000. So that's the kind of iteration that might be involved in the mitigation process. So then on non-wires alternatives, there are more and more of these coming up all the time because technology developers are coming up with new ideas on how they can help with these things. So one, as I mentioned a minute ago, is to use the existing DER, the existing PV, to reduce the load on the system. So then we can have load reduction and voltage regulation by the inverters on the existing generation. Then if we have energy storage, we have, I think, a lot more options because there's more control on energy storage. So again, we can reduce the peak load. We can shift the generation of the PV from daytime to the evening or any other time of the day. We can have voltage regulation, and we can start to look at microgrids. So we may be able to mitigate new transmission lines. We may be able to just improve the reliability or resilience of the system. We can have demand response systems. So again, demand response can help with peak load reduction. We could use it to control a load and prevent some problems with reverse power flow that may occur. We could use it for voltage regulation, but I don't think it's quite as well suited to that. The other problem with demand response is the reliability of the demand response program. So if it's based on something like thermostats, often the customer has the possibility to kind of override the thermostat setting that you want them to use. So for 1 day, it might be okay. For 2 days, less people will want to do it. After 3 days, you may have very little uptake of the demand response program, and I don't know how much you can rely on it. But that's that would be based on the program itself and the data the utility has. So using solar PV, I discussed this a minute ago, so I'm not going to spend a lot of time on it. But we basically want to make conservative assumptions. So we have to assume that the output from the PV is minimum based on historical irradiance measurements. But the other thing we can do is to use volt-var functions from the PV to mitigate voltage problems. And again, this is already in Synergi. It's easy to do. Demand response programs are also something that we can build into Synergi already through the, what do you call them, the custom demand programs, Larry? Yeah. So we can produce these customer demand programs in Synergi that will modify the load throughout the day. Again, we have to discuss the reliability of demand response programs before we implement them in planning studies. And then energy storage. So again, energy storage is much more useful because it's more controllable. And we can have much more assurance about what it's going to do at a certain time of day. So we can use it for the demand profile smoothing. So at the top here, we have an example of an evening peak curve. If we used energy storage, and this is a very simplified approach to it, but we could use energy storage to completely flatten the profile if we wanted to, and if we had enough storage capacity. But at least we can reduce that peak load as much as we need to. Having that controllability also allows us to defer upgrades. We may be able to reduce the, change the time when an overload occurs through a distribution transformer or a substation transformer. And we can look at microgrid applications. So the processes that we have for dealing with these that we've worked through with some utilities, we can help to develop the DER scenarios for a circuit. So figure out which combinations of different kinds of generation and different kinds of technology are required to achieve their goals. So utility may have a goal of reducing the peak load at the substation by 10%. And then we can figure out how much of each kind of generation or how much of each technology is required to do that. And then come up with all the load and generation profiles. So we find those scenarios, make sure the utility can reduce their peak load or whatever by as much as they need to. And then we conduct an impact study. So we have a team in DNVGL that works really on the demand side, the customer side, and just looks at what the customer technology would have to do. And then in our Synergi Electric team, we take that information, we put it on the distribution feeder and figure out what is the worst that could happen, given all the control directives that you have. And figure out if there are still any other violations caused or any other mitigations that we might need. So we can figure out what all of the costs are to get this benefit. And then we conduct that kind of cost-benefit analysis, and we can compare with a conventional solution. So we need to be able to take into account things like if the utility has to invest in DERMS or ADMS to make this technology work, and make sure they're aware of all the costs involved. And then we can do a similar process with microgrid. I'm not going to go through all these steps because they're basically the same. But again, we can help to figure out what the technologies are required, what mix is required, what control directives you'd have to have on them to achieve the goals, and then get eventually to a cost-benefit analysis for the utility. All right, so the last part is on hosting capacity analysis. And I'm sure most of you, if not all of you, are familiar with hosting capacity studies. But there are some new and innovative ways that utilities are starting to use the information and start to use the process. So here we're going to look at two of the hosting capacity analysis processes in Synergi. First, we'll look at the incremental hosting capacity analysis process. So that is for each individual section of your feeder, we figure out how much load and generation could be installed without requiring any upgrades. And it's useful for cases where we have a small number of generators coming online between our planning studies. So usually it's for like utility scale generation. It's less useful for areas where you have a lot of residential generators coming online all the time. And that might be a situation that's more suited to the stochastic hosting capacity analysis. So in the stochastic hosting capacity analysis, we find limits for the feeder as a whole. It's not for each individual section. And it's based on different dispersals of the generation. Because where the generation comes onto the system has a huge impact on whether any violations are caused. So there's a lot of uncertainty about that. We don't always have any idea about where that generation might appear, because customers can purchase and install these things very quickly if they're just putting them on their own homes. So stochastic hosting capacity analysis is good for that situation, but it's less useful for like a deterministic planning process and where we need to justify upgrades on the system. So I'll go through both of those. So incremental hosting capacity analysis, like I said, is on a section-by-section basis. It's useful for large facilities. It's also the kind of information that utilities produce for public consumption, because we can produce these kind of heat maps, and a customer can go and look there, see on this section that I might want to install a generator, how much can I install without any upgrades? And it's very straightforward, very user-friendly usually. We can also use it for interconnection screening. Yeah, that's basically what I just said. So on interconnection screening, we have done some work to figure out what the process might be and how utilities might do this. And what it is helping utilities move towards an online process for interconnection applications, and reducing the amount of resources required from the planning department just to deal with interconnection process. So it would start with a customer making an application online, figuring out their generator size that they want to install and the location. And then we can consult a hosting capacity analysis that has been done recently for that section. So first of all, we need to check the validity of that hosting capacity result that we have. We need to check if any other generation has been installed on the system or added to the queue between when the hosting capacity analysis was done and when this application was made. If there was no extra generation, then that's fine. We can use the hosting capacity analysis result. If there was extra generation, then we have to figure out if that affects the hosting capacity on this section or not. But we can still do that through an automated process. And then the question is, was the section's hosting capacity exceeded or not? So if the hosting capacity for the section is exceeded by this new generator, then we have to go to a supplemental review, start looking at more mitigation that may be involved. But if the generator is below the hosting capacity for that section and we're confident in it, then we could just approve the request. If we were moving to an automated approval process, then we need to have some kind of conservatism in there so the utility can trust the result. But all of this can be automated, from the online application to approval of the request. And we can do it using hosting capacity results, as long as our hosting capacity analysis is set up to provide that kind of assurance. So next is on stochastic hosting capacity analysis. So the result of stochastic hosting capacity analysis is a scatter plot, and I'll show you some in a second. But we get scatter plots for each of the different technical criteria that we look at. So we look at voltages, thermal loading. We can look at power flow as well. And we look at thousands of trials, so thousands of different dispersal of generation, and try and see what the critical cases are. So again, this is suitable for cases where we have a lot of small generators that may come online and we don't know where they're going to come online. So this is a scatter plot of the high voltage from thousands of different hosting capacity analysis on one feeder. And I put a red line in there, which is 126 volts. And so that represents our high voltage violation. And we can start to split this up into different areas. So in this green area, we had none of our trials that produced a high voltage violation. So we could say there's some confidence that up to those generation capacities, even if the generators are dispersed anywhere on the feeder, then we wouldn't have a voltage problem. Then we have this area here where sometimes the dispersal of the generation caused a voltage problem, sometimes it did not. So for these PV capacities, we're not sure what might happen, so we probably do need to do some more reviews if we start to reach those capacities to figure out where is it okay to install the generation. And then we have this last area here where it doesn't matter where this amount of generation was installed on the feeder, there was always a high voltage violation. So in those cases, we probably would need to start looking at upgrades. So the use of these stochastic hosting capacity analysis results is to help with the kind of small generators, the net meter generation, where utilities may not always do individual impact studies for these generators, but you need to be able to account for them to address them. So we can track the amount of net meter generation, the amount of these small generations on the feeder, and start to see when they hit these different ranges, when they're in the green range, when they're in the yellow range, and when they're in the red range, and deal with them that way. So we can say if it's in the green, we can continue to accept those small applications. If it gets into the yellow range, then we need to do more kind of hosting capacity analysis and see where it might make sense to make upgrades or just not allow any more generation. And then in the red area, then we do need to probably install some upgrades before we allow all those generators to be installed. So what we say with any kind of stochastic analysis is there's uncertainty. And uncertainty implies risk because we just don't know exactly what is going to happen. So we need to make sure we do a reasonable number of trials to make sure we're capturing the worst cases for each of the PV penetrations. And the stochastic hosting capacity analysis can do that. It's very straightforward in Synergi. So last few slides here in summary. So again, like I said at the start, modern distribution planning processes are driven by the amount of new technologies, new generation on the system. And it's driving us towards more automation and dealing with much larger amounts of data than we had before. So we need to have some big data processes to deal with that. Things we talked about are on the big data and automation side, we can start to look at the complex interactions of load and generation on the system. We can look at alternative scenarios so we can make different assumptions about what the PV might do, what energy storage might be doing, apply different control processes, and really take full advantage of what we have on the system. On the new tools and processes, most of us start to look at non-wires alternatives, and combinations of technology can help to deal with that. We can start to look at new ways of using hosting capacity analysis, the results, and making benefits for the utility and for the customers. We can produce more interactive tools for the customers, so the interface with them is better. It reduces the amount of resources required from the utility to deal with the customers. And we can look at integrated resource planning processes, which are really now driven by the distribution system rather than be completely separated from the transmission system. We can start to drive the IRP from the DER up, and make sure that we take full advantage of the DER and fully address the costs of them. So I think that's everything I had. So thanks for your attention. If you have any questions, and I think we've got 5 minutes.
5 minutes, yeah.